Hello everybody, this is Andy Pils, and again in the video we're going to be going over how to draw an ellipse and then how to use a calculator to calculate that ellipse's eccentricity. So the first thing that we'll need to do is go ahead and throw two push pins into this piece of paper. Those are our two foci. I'll use this looped string and put it nice and tight in order to draw my ellipse. There we go. And so here's my two foci, focus 1, focus 2. And the length of the major axis is going to be the line that goes through both foci. So I'm a little bit crooked on my page here. So I'll just draw that line in. Make sure it's nice and straight. And there's my ellipse. So the distance between two foci, I'm going to measure that in centimeters. My tripod isn't allowing me to get my ruler in there. So let's see, that's about 3.5, 3.7 equals 3.7 centimeters. And the length of the major axis is 16.1 centimeters. Because again, the equation for eccentricity is the distance between our foci over the length of the major axis. All right, so when I do my math here, since I'm dividing centimeters by centimeters, those units are going to cancel out and I'm going to get just the number for my answer, and then I'll divide 13.7 by 16.1 and get 0.22981. So I would have 0.230 since I'm going to round my number up. Let's try another one of those. I'll use the same line. That way we can compare those two ellipses a little bit easier for my major axis, but I'll extend these two foci out a little bit further. So let's just label this number 1. And now we'll have a smaller ellipse inside with our two foci a little bit further apart. Oh, that's kind of sloppy over there. Sorry about that. Let's pull this nice and tight. All right. So the eccentricity of ellipse number 2 here. Sorry, focus this camera. We're going to do the distance between two foci. About 5.9. Divide that by the length of the major axis. 5.6, 13.7. Let's calculate that. We'll cross out centimeters. See if you can give me the answer before I get to it. I know it's going to be between 0 and 1. Divide 5.9 by 13.7 and round it correctly. So we get 0.4, 3, and 1, since we're going to round up for that last one. So as the distance between the two foci increases, as I went from this first ellipse to the second ellipse, my eccentricity is going to increase as well. So we'll see that one last time. Let's move these foci out a little bit further. Let's see if my string is big enough for that one. Yeah, it should make it. So this is the biggest distance between two foci of these three ellipses. Keep the string nice and tight while drawing my ellipse. I was a little sloppy on that first one too, so here's foci 1 and 2. Let's see, eccentricity of 3. My distance between two foci is about 8.0 centimeters. I'm going to divide that by the length of my major axis. It's about 11.7 centimeters. Cross those out. Equals 0.684. So again, as I increased the distance between those foci that I was using to draw my ellipse, I can see that those ellipses got more and more eccentric. All right, let's take a look at some more examples for calculating eccentricity. So these next two examples are going to come from today's lesson's slide deck. And the question is asking, what is the approximate eccentricity of the ellipse? So first off, I don't have paper and a ruler to do this calculation, but I can do a Google image search and find a ruler. And as long as I'm using the same measuring device and it has the same equal increments, then when I do the math, the proportion will still be the same. So we can search for a centimeter ruler. I like those because they have the smaller increments. So I can use nearest millimeter for a more exact measurement, or 0.1 centimeter. And looking at my choices here, I can already rule out choice 4 because the eccentricity is higher than 1, and we know that that's not the case for ellipses. It has to be between 0 and 1. Now also I know, looking at the distance between these two foci, it seems pretty significant compared to the major axis, so I would imagine that this eccentricity is pretty high, but let's use the ruler to find out for sure. So I'm going to line that 0 increment up with my 1 focus and then measure the distance here. So that's 2.1, 2.2, 2.3. 2.3 is the length of, or the distance between the major axis, the distance between the foci, and the length of the major axis that's going from one end to the other. Try to get it as specific as I can. Oh yeah. And it goes through both foci. Oh yeah. This is tough. There it is. I think that that's pretty accurate there. So it's going through both foci. The 0. Oh yeah. I messed it up. I'm glad I made that mistake. So make sure that that 0 increment mark is lined up with the edge of the ellipse. There it is. And it appears that the major axis is 3.5. So I'm going to do that calculation here, divided by 3.5. And the eccentricity is, I got about 6.6, but it looks like we were right that the eccentricity was pretty high. Let's take a look at one more of these. This one is saying the eccentricity of this constructed ellipse is closest to, so I'm going to calculate the eccentricity, and then we are going to compare it to the data in the ESRT. So for this one, I'll use the same ruler again. Our distance between foci is 0.5, 0.6, 0.7, 0.8. So let's clear this, 0.8 divided by, quicker that time. Looks like we are at just over 3, so I'm going to say 3.1. Divided by 3.1. And the eccentricity is 0.258, so we're going to compare that to the eccentricities. 0.258 would be closest to Mercury's over here, so the correct choice would have been choice 1. So, hope you found this video helpful again. I will see you next week. Take care. Bye.